Good evening, students. So today I will discuss regarding polarity of bonds. As you already came to know, we are in the covalent bond formation. So how the formation of a covalent bond take place? What are the factors that are influencing the formation of a covalent bond? Even including the in the same way ionic bond too also. Dear students, 100% ionic compound or 100% covalent compound, it is an ideal situation. It is an ideal situation. What it means now? In a ionic bond, some percentage of covalent character will be there. Even you take where in a covalent bond, some percentage of ionic character will be there. Ionic character will be there. That was so very difficulty to get 100% covalent or the ionic where in the heteroatomic molecule. That was it is known as an ideal situation. Let us take a few examples. As you already came to know, the molecules like H2, O2, N2. So these are known as non-polar covalent molecules. Non-polar covalent molecules. If you are going to take the hydrogen bond, where in the hydrogen molecule, the covalent bond formation. Listen to me correctly. So what we come across? Between the two hydrogen atom, there is a single covalent bond is there. And the bonded pair of electrons that exactly lies between these two atoms. Why means same atom. These are known as Homo atomic molecule. So both the atoms equally share its electrons, and whatever the bonded pair of electrons will be there, that is equally distributed between these two because same atoms are there. That means bonded pair of electrons that exactly lies in between the two nuclei of these two atoms, where in a non-polar covalent molecules. So because of this reason, there is no polarity at all, no charge separation at all. That means these types of molecules are known as non-polar covalent molecule. Same atoms, no any electronegativity value difference, that one you have to remember. If you are going to take between the two oxygen atom, there is a double covalent bond. Here too also, bonded pair of electrons that are equally distributed, equally shared by both the atoms. No any atom acquires any charge. Again, it will lie between the centers of the nuclei of the both of the two atoms, that one you have to remember. Therefore, hydrogen, oxygen, nitrogen molecule, all these are known as non-polar covalent molecules. Let us take few different examples. If you are going to take hydrochloric acid, HCl. See where in hydrochloric acid, the bonded two atoms, these are not same, these are different. If you are going to take regarding their electronegativity values, hydrogen is 2.21, chlorine is 3. Due to differences wherein their electronegativity values, chlorine atom acquires a partial negative charge, hydrogen atom acquires a partial positive charge. Why? Due to the differences wherein their electronegativity values. You know meaning of the term electronegativity. Tendency of an element to attract the bonded pair of an electron towards itself. Which is being more electronegative element? It pull towards itself. Which one? Bonded pair of an electron towards itself. Therefore, this chlorine atom, it acquires a partial negative charge, delta, small change we can say delta minus, hydrogen atom delta plus. Let us see where in this case there is a charge separation. There is a charge separation. Such type of molecules are known as polar covalent molecules. Polar covalent molecules. Polar covalent molecules. Why? Bonded pair of an electrons are attracted towards more electronegative atom side. That one you have to remember. If you are going to take non-polar, what I said, hydrogen molecule, non-polar, whatever the bonded pair of an electron will be there, shared pair of an electron, that will be equally distributed by both the atom because these are same atoms. This bond pair of an electron lies between the nuclei of both the atoms. That means there is no any charge separation, hence non-polar. Now, if you are going to take regarding water molecule, what we come across here in water, H2O. Whether there is a charge separation or not, that one now we will discuss. So this is oxygen atom, hydrogen, hydrogen. Even you came to know that one there is a presence of a two lone pair of electrons. There is delta minus. This is delta plus. Why? Oxygen atom being more electronegative, this bonded pair of an electrons are attracted towards more, which side? Oxygen. So two OH bonds are there, that was about delta minus. There is also a slight charge separation in this molecule, that one you have to remember. So delta minus I wrote. Okay. This is also polar molecule, that one you remember, polar in nature. So what it means? We are in a homoatomic molecule. So when the bonded pair of an electron, if it lies between the nuclei of the two atoms, centers of the nuclei of the two atoms, then no any atom acquires any charge. But in heteroatomic molecule, like you take HCl, so water molecule, or even you take ammonia, or even you take hydrofluoric acid HF, all these, due to differences wherein their electronegativity value, so bonded pair of an electron is attracted towards more, which side means electronegative element side. Here oxygen being more electronegative, hence it acquires partial negative charge. Hydrogen atom, partial positive charge, that one you have to remember. These are all known as polar molecules. The very interesting thing is, whether the given molecule, covalent molecule you take, is it a polar or a non-polar? How that one is determined. Even if you are going to take methane or carbon dioxide, two examples I am giving, whether these two molecules, these are polar or a non-polar. So your answer will be, so carbon and oxygen, there is an electronegativity difference. You may think both seems to be, what do you call, polar in nature. Why? Carbon and hydrogen, difference in their electronegativity value. But both these two molecules are non-polar student. Non-polar student. Then question arises, how and why? How, why? Then actually, which one measures the degree of polarity wherein a molecule? Degree of polarity wherein a molecule. Because there is a partial charge separation between the two bonded atoms. Correct? Then such types of molecules are known as a polarized. But here too also you can see there is a difference in their electronegativity, but molecule seems to be non-polar. Therefore, degree of polarity wherein a covalent molecule, that is expressed in terms of one of the important concepts that is known as dipole moment. Dipole moment. So this dipole moment, it measures the degree of polarity. What is that one now? Dipole moment. It measures the degree of polarity in a molecule. What is that dipole moment? what are its unit? So all these things that for now we will discuss. Let us take AB molecule. This is A atom and B atom. This is Q plus, Q minus. Both these are get separated by distance of separation between these two atoms. That is R I will take Q plus and what I wrote now Q minus. Better the product also we can write in this way also we can take. So we can write. This is R we can take. Now dipole moment. Dipole moment, it is the product of the magnitude of charge of positive or negative charge and distance of a or distance where from a center of we can take the positive and negative charge. That is known as dipole moment. Or in a simple sentence, we can define in this way also. What is that one? The product of the magnitude of the charge and distance of separation between the charge, that is also known as dipole moment. While defining the terms here, definition, the product of magnitude of what I'm taking positive or negative charge. There is nothing but Q. The product of magnitude of positive or, this is very important, or negative charge and distance between the centers of positive and negative, here I wrote and negative charge. That is known as dipole moment. In simple sentence, the product of magnitude of charge and distance of charge separation, that is also known as a dipole moment. Here what I wrote, magnitude of positive or you take a negative charge and distance between the centers of positive and negative charge, that is known as dipole moment. So mathematically, this dipole moment that is given by this expression, which is that one. So it is denoted by the Greek letter mu. There is nothing but dipole moment. Dipole moment is equal to what I have to take now? Where in this formula? First charge. That is nothing but Q. That is charge on any of the atom you have to consider. Charge on any of the atom. Multiplied by distance between the two atoms. This is plus Q, minus Q have been taken. So this is the distance between the two atoms. Distance between the two atoms we can take, or distance of separation. So if you are going to take charge Q, this is nothing but R. So this is dipole moment. Q into R I took, where R is known as distance of charge separation, also we can say distance of charge separation. Q, so what is that one? Charge on any of the atom. Okay. Now, if you are going to take the value of Q, if charge, that is Q, it is of the order that is equal to 10 to the power of minus 10 electrostatic unit, ESU. So what I'm taking in this case now? So it is of the order how much now? So 10 to the power of minus 10 electrostatic unit. And if you are going to take regarding the intermolecular distance, intermolecular distance, it is nothing but R. It is 10 to the power of minus 8 centimeter. Or even we can take one extra unit in terms of centimeter I am taking. Now, product of these two. What I have taken? Charge on any of the atom, any one of the atom. Therefore, your dipole moment equal to, what I have tried now here, that is Q into R. So, this is Q is nothing but 10 to the power of minus 10 electrostatic unit. So, R is nothing but 10 to the power of minus 8 centimeter. Product of these two, 10 to the power of minus 80 electrostatic unit centimeter. You know this electrostatic unit centimeter, that is known as 10 to the power of minus 80 electrostatic unit centimeter, that is known as 1 d by 1 d by. Therefore, unit of dipole moment is d by. So what we can write now? 1 d by that is equal to 10 to the power of minus 80 electrostatic unit centimeter we can write. So now coming to the SI unit of this dipole moment, student, 1 d by. So what we have to write where in this case? So unit of dipole moment is d by. 1 d by equals to 10 to the power of minus 80 electrostatic unit centimeter. DE by E 1 d by. Okay. Now see here. SI unit is very important. SI unit of dipole moment. What is that one? If I want to take, so one is d by, that one we are expressing in terms of coulomb meter, student. Coulomb meter. How much it is now? Where in this SI unit? If I want to consider, so this is equal to 3.335 into 10 to the power of minus 30 coulomb meter. This is SI unit. So we are expressing in terms of coulomb meter. That one you have to remember. So even what we can write in this case now, so coulomb meter. Sometimes you may think no centimeter like that. Don't get confused. Coulomb meter only. So this is 1 g by. That is exactly so 10 to the power of minus 18 electrostatic unit centimeter. Here, so what we come across. So if you are going to see the SI unit, you have to multiply whatever that one given 1 divided. You have to multiply by. So here I will write 3.335 into 10 to the power of minus 30 or 3.3 enough now. So during the multiplication, don't go for 3.335, you may get a confusion. 10 to the power of minus 30 coulomb meter. Okay. So these are the things that you have to remember. Now I will take a few examples how this dipole moment measures the polarity in a molecule. Which types of molecule? Covalent molecule. That one now we will discuss one by one. So we will go for the first example. See here, which is that one I will take. So known to unknown example, we will discuss where all these students. First one is hydrochloric acid, HCl. Here, just I will show you how this dipole moment that one is represented. Dipole moment, it is a vector quantity. First you have to remember vector quantity. vector quantity. Vector quantity. Because it is having so magnitude as well as also direction, that one you have to remember. Now HCl. Okay. The way of representing this dipole moment wherein these molecules. I am taking electron density arrow mark. See here. Where from? We can see here. Where from? A cross tail with the arrow headed towards the side. The more electronegative atom site. This is less electronegative, or even this is to be treated as electropositive atom. That one you have to remember. Therefore, if you are going to take this one as a vector quantity, so way of representing where on the molecules, that one we are representing in this way. Electron density, so where from less electronegative towards more electronegative side, positive center towards negative center, that one you have to remember. And very interesting things here, a small arrow with the tail has been taken pointing towards which side? Head. So more electronegative atom side. This is the way of representing the dipole moment, that one you have to remember. Suppose if it is a molecule, or in that molecule if there is a lone pair of electrons, how you are representing? We are representing or showing this dipole moment. So that one also I will take. You know, ammonia molecule. Okay, see here. Here, there is a presence of, let us see here, lone pair of electrons. Orbital dipole, due to the presence of the lone pair of electrons, we have represented a tail pointing towards this side. You have to represent this one in this way. From again, so less negative to more electronegative atom side. Way of indicating dipole moment for a orbital dipole containing lone pair of electrons. This is the representation. But in this case, see here, if you are going to consider hydrogen and nitrogen atom, which is more electronegative? Nitrogen. The point of showing the directions here. 1, again 2, again 3, like this. What we come across in this case means, always one thing you have to remember wherein this, a small arrow with tail have been taken, where at the positive center, this class is the positive center towards the negative center side. That is the representation of dipole moment. Because dipole moment is a vector quantity, that one you have to remember. So it has direction as well as also magnitude, that one you have to remember. Okay. Now coming to dipole moment values. Already you came to know SI unit of dipole moment is Coulomb meter, that one you have to remember. Okay. Now first example, where in this I will take beryllium chloride, student, BeCl2. Is it a polar or a non-polar? If you are going to see the electronegative difference between these two, chlorine is more electronegative. Maybe there is a charge separation, but this molecule is non-polar in nature. Why? Dipole moment value is 0. If the dipole moment value is 0, then it is non-polar, student. If the dipole moment value is not equal to 0, means it is having a value, then it is known as polar. Again I am repeating, degree of polarity wherein a covalent molecule, it is expressed in terms of this dipole moment. Actually it measures the polarity in a covalent molecule, not just merely by seeing the differences wherein the electronegativity values, that one you have to remember. Now if you are going to take beryllium chloride, beryllium fluoride, let us see here. Beryllium is the central atom. Now fluorine, here also fluorine atom have been taken. Same environment, we can write both these two examples. Now if you are going to see here, showing point of directions, where from positive center towards negative. Yes, this is here. Okay. Two beryllium fluorine atom, two beryllium and fluorine bond will be there. If you are going to know about this one, it is having a dipole moment. It is having a dipole moment. But see there, both these are acting which direction? Opposite direction. Opposite direction. Individual bond, if you are going to consider this one, beryllium fluorine atom bond, if you are going to consider X, there is a polarity. Dipole moment will be there. But one more fluorine atom, see, this is acting in opposite direction. Because of that reason, arrow mark just you have to see correctly. Because of this reason, net resultant dipole moment, which is acting where on the beryllium atom, it is equal to 0. Therefore, it is a non-polar. Non-polar. That one you have to see, non-polar. Even if you are going to take water molecule, that is, again, I will go through the water molecule only. See what happens where in a water molecule, H2O. All these are polyatomic molecule or heteroatomic molecule because different atoms are there in that molecule. That one you have to remember. H2O student. Okay, this is the oxygen atom. Again, hydrogen atom, hydrogen atom. You may have a doubt. Sir, two lone pair of electrons are there, no? Yes. Now this one you have to take in this direction. So this is in this direction. Lone pair of electrons. Orbital dipole due to the presence of two lone pair of electrons. See how you are representing. One is acting in this direction. This one is acting in this direction. Okay. And what about this? If I want to take C, yes. Net resultant dipole moment. See the direction. In this way. Both of these get cancelled. These are in the opposite direction. Now, net resultant dipole moment it gets added. Because of that reason, your water molecule, it is having a dipole moment value student. How much you know the Besser dipole moment value? That is equal to 1.85 dBi. Then question arises, how to convert this one in terms of Coulomb meter? What you have to do, student, you have to use the conversion factor. 1 dBi equal to 3.3 into 10. Don't take 3.335 something I wrote. 3.3 into 10 to the power of minus 30. Just you have to multiply, that is in terms of Coulomb meter. Therefore, mu equal to 1.85 multiplied by 3.33 into 10 to the power of minus 30. Now, Coulomb meter. Then exactly how much you will get now in terms of a Coulomb meter after multiplying. That seems to be 6.17 into 10 to the power of minus 30. 10 to the power of minus 30 Coulomb meter. Now what you have to do for remaining, no? If it is given in terms of dBi, so 1 dBi equals to 3.335 into 10 to the power of minus 30 Coulomb meter. So you have to multiply, you will get in SI unit. Usually we are expressing whatever the data that are given in terms of a dBi unit only, that we have to remember. This is when for water molecule. What we come across in this case for water molecule? 1.85. So here, in most of the textbook, these two lone pair of electrons will get cancelled. So it is given in this way only. Exactly you can see. So now we are representing net resultant dipole moment. Both these two OH bond dipole moment gets added. Because of that, it is having the dipole moment value 1.85 dBi. Is it a polar or a non-polar? Yes, it is a polar. Why? So dipole moment value is not equal to 0. That one we can see. You have to remember. Now coming to the next one, I will take a known example. Which is that one? All of you know carbon dioxide molecule. Yes, everybody you know carbon dioxide molecule, CO2. So my question is it a polar or a non-polar molecule? Which one? CO2, carbon dioxide molecule. Now, which is the central atom? Carbon. Yes. Leave over the lone pair of electrons now. Just CO2 I wrote. Now, which is more electronegative? Which is more electronegative? Here, if you want to represent here, oxygen is more electronegative. In which direction both of these are? This is CO bond and this CO bond, both are acting where in a opposite direction. Both are acting where in a opposite direction. So what we came to know, where for this carbon dioxide molecule, whether it is having a dipole moment value, how much? If you are going to take regarding C double bond O, it is having the dipole moment value. Exactly how much means it is 2 dipole moment, 2.3 we can get given. But see there, both these are acting in which direction? Opposite direction. C double bond O bond. So it is okay. It is a, we can see a bond, polar bond only we can consider. But both of these are acting very opposite. Net resultant dipole moment which is acting on this atom, it is 0. Hence it is a non-polar in nature. That one you have to remember. So individually, if you are going to consider, it is having a dipole moment. Is it correct? But both are acting in the opposite direction. Therefore, it is non-polar. Now coming to the next example. So which are all these? If you are going to consider boron trifluoride, BF3, is it a polar or a non-polar? That one also we will discuss. The central atom is boron. Now, 1, 2, 3. Okay. Better now, no need to go for the geometry now itself. Okay. So see here, fluorine atom seems to be more electronegative. Because of its symmetry, because of its symmetrical arrangement, around the central atom, similar atoms are bonded. Similar atoms are bonded. Hence, because of its symmetrical arrangement, again, dipole moment value is 0 for the boron trifluoride. That one you have to remember. Now, I will take the two important examples. Among these, which molecules are possessing higher dipole moment? That one now we will discuss. Dear students, you know again ammonia. That was I did not put any data for this. And one more I will take nitrogen trifluoride. Here hydrogen atom. In this case, hydrogen is replaced by fluorine atom. Let us see pyramidal geometry. But regarding the geometry, after completion of the hybridization only, I will go through all these. Anyway, now 1, 2, 3. 3 NH1. Okay. Now, one lone pair of electrons. Coming to this one, nitrogen trifluoride. 1, 2. This is 3. Fine. Now, in this case, see here. This is orbital dipole due to the presence of a lone pair of electrons. Nitrogen seems to be more electronegative. Okay. In this case, fluorine seems to be more negative as compared to nitrogen atom. See, electron density, where from the, so less electronegative to more electronegative side. Yes. Now coming to the values. Among these two molecules, which one is having higher dipole moment value? This is given 1.47 dpi. Where for nitrogen trifluoride, if you are going to consider 0.24 dB. Why it is like that? Both the molecules are having one lone pair of electron, one lone pair there at the apex of the nitrogen atom. Okay, fine. But here hydrogen, three atoms are there that are bonded to the nitrogen. Here fluorine atoms are bonded. If you are going to take this one, all the three NH bond, their resultant dipole moment, it is acting. Which direction? In the direction of the orbital dipole due to the presence of a lone pair of electron. Hence, everything is get added in this direction. In this direction, everything is gets added. All these three added along with the orbital dipole due to the presence of a lone pair. Because of that reason, so dipole moment 1.47 dB. So again conversion factor. Now I will not say, just you have to multiply 1.47 into 3.33 into 10 to the power of minus 30 coulomb meter. So you have to multiply right here. That is in terms of coulomb meter. Here why it is less? Dear students, see this one. This NF bond dipole moment and this one is again opposite. Here orbital dipole moment and this NF bond dipole moment both are in opposite directions. Even some of the value get nullified, but it's not equal to 0. It is equal to 0.24 dB. Because of that reason, what we come across means ammonia is having higher dipole moment as compared to which one? Nitrogen trifluoride. Dipole moment of which one? Ammonia is greater than nitrogen trifluoride. That one also you have to remember. Now, very interesting, few of the molecules I will take. Later on, we will go for the, which is that one means the importance of this dipole moment, where we will see. Dear students, you know our methane molecule. Yes. Is it a polar or a non-polar? Then in your mind, suddenly it arises, sir, difference is their electronegativity. It may be, you may think polar, but it is not a polar. It is a non-polar. Why? Because of its symmetrical arrangement. Let us see here, carbon atom. 1, 2, 3, or 4. So you come across regarding the tetrahedral arrangement. But very interesting thing, see here, where in this case. Now, what we come across? 1, 2. Yes, symmetrical arrangement, that one you can see around the central atom. Because of the symmetrical arrangement, whenever where around the central atom, if same atoms are there, 100%, it results in the formation of a zero dipole moment. Hence, it is a non-polar. That one you have to remember. Not a polar, non-polar. Symmetrical arrangement. Even I will take in the same way one more example, which is that one. What about this carbon tetrachloride, CCl4? Is it a polar or a non-polar? Here too also you can see around the carbon atom again 4 chlorine atoms are there. Tetrahedral arrangement. Let us see here. Now, which is more electronegative? Chlorine atom. This direction, again this direction, again this direction. Okay. Here too also what happens now? Because of its symmetrical arrangement, this molecule is also having zero dipole moment. Hence, it is a non-polar. Non-polar. Okay. Now I will take in the same way one more example, student, which is that if you are going to consider chloroform, CHCl3, chloroform. Whether this chloroform is it having dipole moment value? Is it equal to 0 or not equal to 0? 100% it is not equal to 0. Why? No need to say again regarding the what? Datas. Okay, let's see here. Carbon, hydrogen, chlorine atom, this chlorine atom. Here what we come across, this is more electronegative. See, the centers of photo carbon, positive center towards negative center iso. Now in this case, this is in this case, student. When these are going to get cancelled. Cl2 bond get cancelled. This is going to be added. Therefore, it is having the dipole moment value. That one you have to remember. So that means I am writing it is not equal to 0. It is having some value. Hence, it is a polar in nature. This is non-polar because of its symmetrical arrangement. Now coming to the what are the important importance of this dipole moment or application of a dipole moment. So I already again said, again I am repeating, which is that one now. Importance of dipole moment. Here I will write importance of dipole moment. So better I will take here the importance of dipole moment. So what we come across? The degree of polarity in a given molecule that is expressed in terms of dipole moment. This dipole moment, it measures the polarity in a molecule. If dipole moment value is 0, then we have to say non-polar, not equal to 0. It is polar in nature. What are the importance? First importance of this one. So see here, to differentiate between polar and non-polar molecule. To differentiate between polar and non-polar molecule, I wrote. How? Very simple. If I am going to write EH2, O2, N2, methane, carbon dioxide, all these are non-polar. The reason for this one is their dipole moment value is 0. On the other hand, I will take, which are these? Water, chloroform, even you take ammonia, or even you can include nitrogen trifluoride. Is it correct? No. And all these are possessing what? So dipole moment value not equal to 0. Hence these are known as polar. So to differentiate between polar and non-polar molecule. Now coming to the second importance of this dipole moment, which is that one. So even we can predict the degree of polarity. It is very important. Degree of polarity in a molecule. One simple example I will tell you, students, how it measures the degree of polarity in a molecule. See here, HF, HCl, the next one is HBr, HI. There I did not say anything regarding what? Their dipole moment values. If you are going to consider differences wherein their electronegativity value between the combining atom is more, there will be a very large charge separation and there will be higher polarity. Higher the polarity in a given molecule, higher will be the dipole moment. Because this is 2.1 electronegativity value, chlorine 4. What about chlorine? So if you are going to consider regarding the chlorine atom, that is equal to 3. This is 2.8. And if you are going to take regarding the iodine atom, that is 2.5. 2.5. So where will be the more differences where in the electronegativity value in hydrofluoric acid? Hydrofluoric acid, HF, hydrogen fluoride. So here degree of polarity what happens? Increases. Due to the increase where in the degree of polarity, dipole moment value also increases. That one you have to remember. Even we may write. So one conclusion we can draw where from this dipole moment is directly proportional to differences where in the electronegativity of the combining atoms. Higher the electronegativity between the combining atoms, higher will be the charge separation, higher will be the degree of polarity, higher will be the dipole moment values that we want to remember. Now, what about the dipole moment? Where the HF molecule, if you're going to consider, it is 1.78 dpi. Again, conversion factor we have to go through. Next one is HCl. If you are going to consider for hydrochloric acid, so the measured dipole moment value is 1.07 dpi. That one we come across. Next, 0.79 dpi in hydrogen bromide. The last one is so roughly 0.38 dpi. So more the electronegative difference we can see in hydrochloric acid. That means higher will be their dipole moment value. Dipole moment value 1.78 dpi, 1.07 dpi. This data may be varied, students. Don't think about the data, only generalization. Why means I said already, dipole moment is directly proportional to differences wherein their electronegativity value. Higher the difference wherein the electronegativity between the combining atoms, higher will be the dipole moment value. That we have to remember. Now, one more simple importance or application also we can say, which is that one. If you are going to consider the geometry of the molecule, is it possible to predict? Is it possible to predict where from this dipole moment? Yes. Third importance. What is that one? Geometry or shape of the molecule. Is it possible to predict geometry of this molecule? Let us see where in this case, if you are going to take only two examples, no, carbon dioxide and water molecule. Again, I will explain regarding the geometry, where in the remaining concept. Don't now think much more regarding the geometry, how and why. But based on the dipole moment value, see here, central atom carbon. So you came to know that one double bond is there. I am not representing the lone pair of electrons. Okay, if you want this, I will write here also, no problem. No problem. Okay. But see there, this C double bond O bond, it is in this direction. Then 0. Exactly how much in the degree? 180 degree. 180 degree. When it is 180 degree, it is linear. It is linear. Linear in nature, that we have to remember. What about our water molecules? See here. Bent. Even we come across bent shape. This is linear shape. Why? Dipole moment value. It is 1.85 divided. In some text it is given also 1.84. Don't get confused. So this is bent. This is linear. Even it is also known as V shape also, bent shape also. Okay. Now even we can predict the geometry of the molecule. So coming to the next is very important, the uses of this dipole moment. Listen to me very carefully, which is that one. Now, ionic character I am taking, ionic character in a covalent molecule. Is it possible? Is it possible to see the ionic percentage? Ionic percentage. See, if you are going to consider regarding the ionic character in a covalent molecule, what it means, no? To get a 100% ionic or 100% covalent character, it is an ideal situation for a heteroatomic molecule. In a covalent molecule, certain characteristics of certain percentage of ionic character will be there. In a ionic bond too also, certain percentage or characteristics of, even you can see covalent percentage. But how we are determining ionic character in a covalent molecule? Generally, we come across what is that one. So one thing just you have to see, remember what I'm telling see here. If you are going to take two atoms that are covalently bonded. Which are these two? A and B are there, covalently bonded. Correct? Here, the differences were in their electronegativity value between the two combining atoms. If it is exactly equal to 1.9, that is difference in their electronegativity value 1.9. What we come across? 50% of ionic character and 50% of covalent character. When means electronegativity difference between the two combining atoms, if it is 1.9. Most of the students you know that in some textbook it's not given 1.9, it is given 1.7 also. 1.7 also. Okay, that was I'm telling. Don't see the data. So 1.7 means again we can predict now. So less than 1 point. No, I have taken as a 1.9 value. Correct? If it is less than 1.9, what have to predict now? More. The covalent character will be there. If it is more than 1.9, 2, 2.5, obviously the percentage of what ionic character will be more. So don't be think that one, sir, is it the standard values? So here 1.7 also given in certain text. So I will take a 1.9 electronegativity difference between the two combining atoms. So 1.9 exactly 50-50. So 50% ionic, 50% covalent. That one you have to remember. Now coming to the very important formula I will give you. Try to understand this formula. Now we will go for one numerical problem. How to calculate the percentage of ionic character in a covalent molecule, student. Covalent molecule. So now, if you are going to take regarding this ionic character in a covalent molecule, the percentage of ionic character that is given by percentage of ionic character is given by dipole moment, where for observed dipole moment for the given molecule divided by dipole moment for 100% ionic character multiplied by 100. This formula we are using. It is a shortcut formula. Even I will write this one, percentage of ionic character, student. Ionic character. This is equal to what I wrote now? Observed dipole moment. In words I will write simply. Observed dipole moment. Dipole moment divided by what I wrote now? Dipole moment for 100% ionic character. So dipole moment divided by dipole moment. Wherefore we have to write where in this case for complete. For complete, we have to take which is that one means ionic character. Dipole moment for 100% ionic character or complete ionic character. One are the same. Again, you are multiplying by 100. That means see there. Observed dipole moment divided by dipole moment for 100% ionic character multiplied by 100. Instead of that, observed dipole moment divided by ionic dipole moment for 100% ionic character multiplied by the 100. You will get ionic character. Now, one numerical problem I will take. One important numerical problem afterwards. So I will start for the D. So which is that one? If you are going to see the hydrofluoric acid HF molecule, I will take. All of you see here how we are determining that one. Calculate the percentage of ionic character ionic character and covalent character. Both I am writing, ionic and covalent character. In a, which molecule I am taking, students? Character of a hydrofluoric molecule. HF molecule I am taking. Having bond distance that is given. Bond distance. How much it is of the order given means 0.92 angstrom unit that is given. And a dipole moment and observed dipole moment, it is also given. How much it is means 1.78 divide. Now one more thing here, Q value is given. Q stands for what? The charge on an atom. Okay. So magnitude of the charge on any of the one atom. Q value is given. How much now Q? That is 4.8 into 10 to the power of minus 10 electrostatic unit. This much is given. Listen to me now. Calculate the percentage of ionic and covalent character of a HF molecules having bond distance. How much it is given? 0.92 angstrom and observed dipole moment is 1.78 dBi. That is given 1.78 dBi. Dear student, you have to see the unit. When the observed dipole moment value is given in terms of dBi, then you have to calculate which one dipole moment for complete 100% ionic character. That is also in terms of dBi. Unit is very important. I will go for the calculation part. Let us see here. This is asked where in the competitive exam. Solution for this given thing is, what is that one? Observed dipole moment. Dipole moment. How much it is? 1.78 dBi. Next one is given. Which is that one now? The bond distance is given. Bond distance 0.92 angstrom unit is there. Okay, now what I will do means I will convert in terms of centimeter. Don't go for meter. So when you have to go for meter, if it is coulomb meter, then you have to go for the conversion. Here 0.92 into 10 to the power of minus 8 centimeter. This is bond distance. Now coming to the formula. So what we have to calculate first? Dipole moment for 100% ionic character we have to go through. Observed dipole moment is given. So ionic dipole moment for 100% ionic character. So now this is equal to, what is the formula again? Q into R. Sometimes Q value will be not given, it is understood. How much we have been taken in this case now? That is 4.8 into 10 to the power of minus 10 electrostatic unit multiplied by bond distance 0.92 into 10 to the power of minus 8 centimeter. So this is equal to 4.8 into 10 to the power of minus 10. Sorry, here you have to multiply with 0.92. This will become 10 to the power of minus 18 electrostatic unit centimeter. Electrostatic unit centimeter. Now how much you will get now? This is 4.416 after multiplying these two. 4.416. So you will get. This is 10 to the power of minus 18. So ESU centimeter. This is 4.416 dBi. I will read. You know the conversion factor. So what is that conversion factor, student? How to multiply? See 4.416 10 to the power of minus 18. This is to be taken as how many? 1 dBi. Now 1 divided equal to, you can see now, 10 to the power minus 18 electrostatic unit centimeter. Okay, 4.416 I wrote. Now coming to the formula. So now I will write the formula. After this I will stop. So what is that one? Percentage of ionic character. Ionic character. So what is that one here? Percentage of ionic. Observed divided by ionic. Dipole moment observed divided by ionic. I will take student. Ionic. Multiplied by 100. Now in this case, I will substitute the values, which is that one. See here. Observe how much it is given now. 1.78 divide. This is 4.416 divide into 100. 4.416. So how much you will get? So this is equal to. This is equal to. This is equal to, if you are going to simplify, no, that is 40 point, more or less we will get 40.3%. That is just to go through now, 40.3% that one you will get. Now this is what? Percentage of ionic character in HF. What about the percentage of covalent character in HF, hydrofluoric molecule? That is 100 minus 40.3. That is equal to how much now? If you are, so how much you will get? More or less means 59.7%. What you have to add? 59.7%. That means even you may have a confusion. Let us see this HF. So this is electronegativity value is 4. This is 2.1. Correct? Then difference if you are going to take, no, how much it is? 1.9. Then I said something, no, that given values 1.9 is 50-50. Britannia, is it no 50-50? Is it 50-50? Where from the given data we can't say 50-50. But generally, so not by taking this one, even we can go for. So general trend, what we come across means by taking a different one could do also. So if the electronegativity value, the difference between the two combined atom is 1.9. So 50% of ionic, 50% of covalent we can see. But from the given data, if you are going to calculate, no, what we come across? Percentage of ionic character in a hydrofluoric molecule, 40.3%. Just you have to do this calculation part. Is it exactly correct? There is 40.3 or not? That one you have to check. So next, percentage of covalent character in hydrofluoric acid, 59.7%. That one you have to remember. So now I will stop where for the today's class. If you are having any doubt related to today's class, you can post your question where in a chat box. Thank you, students.